Hi everyone, my name is Zheng Xiang. Thanks a lot for attending my presentation. Here is the overview of my project. My presentation topic is Improve Head Tracking for MRCam, a virtual reality app to learn spatial layout for the visually impaired. My mentor is Professor Tang. We are from BMCC. Our research project tries to help the blind people to build mental map using augmented reality and encourage their independent travel. The mixed reality cam, also called MRCam, has been developed by our research lab last year. It utilizes simple auditory and haptic feedback on an iPhone to help visually impaired interact with virtual objects and environments as they are working in real-world situations. The visually impaired can learn the physical layout of unknown environments using MRCam mobile app. For example, it allows students with eye disabilities to learn a layout of BMCC fitment hall in their backyards. The four figures explain how the MRCam works. However, we found that users sometimes have difficulty understanding the orientation of virtual objects in the VR facility. Because iPhone mounted on the long can only check can's movement, therefore we cannot check user's head movement. The 3D audio feedback is generated based on the relative orientation and the distance between object and user. When head orientation of the blind user isn't correctly checked, 3D audio can't be played correctly, so the user has difficulty understanding the correct spatial layout. During COVID-19, we were only allowed to conduct user study remotely. During the remote user study, we have to communicate with the blind user through a second phone. We were not able to observe the user's body movements, which made it very difficult for us to understand users' challenges when using our apps and where the user gets stuck. In this study, first we improved the estimation of users' head pose by using iPhone's front camera. It's a challenging task because the MR can already use the back camera to check the environment in order to compute the simulated can's location. Now, we propose to use both front and back cameras simultaneously. We use users' eyes as anchors to check face orientations. The MR can check the actual direction of head based on the change between the anchors and the real environment. The line charts show experimental results. They are my face heading directions with respect to time. When I move my face in different directions, for instance, the left chart shows the head moving angles when I rotate my head clockwise and hold can still. The result is very accurate. When user using the MRCam app, the app will show the data of targets and the user's coordinates and visualize three different views, including camera's view to obtain the movement of the users relative to the real physical environment. User's head view for observing user's heading movement, and the top-down view for getting the translation of user's coordinates in the virtual environment. Through the experiment, we proved that the front camera and the back camera are under one unified coordinate system. It uses the data collected by the rear camera instead of front camera to calculate the user's location. It makes the user's movement in the virtual room more accurate, and we can get detailed users moving trajectory and accurately detect head movement. We apply this algorithm in the MRCam. Time comparison figure shows the average time to find a virtual objects was reduced from 124 seconds to 94 seconds, around 24% decreases. After using the new algorithm, we also found the 3D audio feedback is greatly improved due to the purpose of head tracking algorithm. For the second research problem, we integrate and render the virtual space with Google Map. It allows us to monitor the user's both physical and virtual movements remotely in real time. Based on this, we are allowed to test the app with the blind subjects, and we aim to submit our work to an international conference in human-computer interactions. Thank you so much for attending my topic.